Proportions are equations that have fractions in them. A fraction equals a fraction. Let's start with this example. This is a very simple example. Typically in a proportion, what we do is do the cross product, which is equivalent to multiplying by the common denominator of the fractions. So let's do that. There could be more to that. We should really multiply by the least common denominator of the fractions. But in this case, the least common denominator is just x minus 2 and x minus 3. So we just cross multiply, and that yields to the same thing. So we end up with 4 times the quantity x minus 3 equals 5 times the quantity x minus 2. Remember, all of this is being multiplied with 5. Distribute for x minus 12 equals 5x minus 10. Subtract 4x from both sides of the equation. So we end up with x. While we are doing that, we can add 10 to the other side of the equation, and we end up with negative 2. This is a very, very interesting problem. Let's just double check. Negative 2. If we plug in negative 2 for x, we end up with negative 8 minus 12 is negative 20. Negative 2 here times 5 is negative 10, minus 10 is negative 20. So it appears that this is the solution. However, notice that, oh, yeah, it is the solution. I thought for a moment that this was positive 2, in which case that would not work because 2 cannot be a solution since 2 minus 2 would be 0, and we may not divide by 0. But we do end up with x equals negative 2. So this is the only solution to that proportion. And there we have it. By the way, anytime you have percentages, we are dealing with a proportion, because percentage is the same thing as dividing by 100. You know, like 13% is really 13 over 100. Yeah. So that is pretty much about it about proportions. Proportions are fairly straightforward. Practice them. Make sure you know how to handle them. Let's talk about variations. There are different kinds of variations. And what variation means is how 2 or more variables correlate with one another, how they interact with one another. We have direct variation. That's one kind of variation. We have, you would think indirect, but actually it is called inverse variation. And then we have joint variation. And then we have a combined variation. We're really going to mostly be involved with direct and inverse. Joint and combined, we're not really going to do too much with those two, at least not at this point. I just want to introduce the concept of variation. So direct variation, in direct variation, we may have one input and one output. And the idea is this: if the input doubles, so if the input versus the output, if the input doubles, then so does the output. Doubles. If it triples, then so does this, and so forth. So that's what we mean. You know, if it's 4 times as much in the input, then we have 4 times as much in the output. That's what direct means. They are essentially proportional. You know, so if we are paid by the hour, the more we work, the more we make. If we work as double the hours, then we make double the amount of money. That's assuming that there is no overtime. Okay, and then we have the inverse. The inverse variation is distinguished from this one because let's talk about the input and the output. If we double the input, then guess what? The output gets halved. Halved. There you go. If we triple the input, then the output gets third. Or thirded, whichever way you want to say it. And if we multiply by 4, the input, the output gets divided by 4. So that's why it is inverse. It does the opposite as the direct. The direct, you double one, you double the other. Here, you double one, you actually have to do the opposite, half the other. And by the way, those are reciprocal. So if you double the output, you have to halve the input. In joint variation, we would have 2 of those. So we would have actually 3 variables. And in combined variation, we may have, again, 3 variables, maybe a direct and an inverse happening at the same time. Perhaps we will see some of those, but let's see how far we go in this video. Okay. So in direct variation, so let's do an example. Yeah. Well, let me tell you more about this. In direct variation, we have y equals some constant times the input. That is the basic equation of direct variation. In indirect variation, on the other hand, y is equal to, there's a couple ways to write this down. K times 1 over x. That is basically the way we write. Although a lot of people rewrite this as k over x, a constant over x. Yeah. So here we're multiplying with x, while here we're dividing by x. And they don't tell us the k directly. Most of the time, this is called the constant of variation, constant of inverse variation, constant of direct variation. They don't tell us that. We have to do the experiment once, or they have to tell us one initial piece of information so we can determine the k. So let's start with an example of variation. So assume x and y are in direct variation, or they vary directly, as another way to say it. When y equals 3, then x equals 5. Or sometimes they say when x equals 5, then y equals 3. It doesn't matter. The point is that the 2 of them are together, period. So then we can ask, what is y when, okay, let's do 2 parts. Part A, which is going to be super duper easy, when x is 10, question mark. Okay, so what is y when x is 10? Well, mind that we are in direct variation. So you have to pay close attention to this, direct variation. So when x is 10, well, when x is 10, that's double 5. And in direct variation, if one doubles, the other one doubles. And if, whatever happens to one as far as proportions, then the other one is the same. So if this doubles, that means that the y has to double. When x is 5, the y is 3. So that means that when x is 10, y has to be 6. Just so we don't even have to set up an equation, we can simply say, oh, that's double, so that has to double as well. So y equals 3, and we're finished. That's actually an easy problem. The difficulty happens when it is not as obvious. If we put 15 here, you would know, oh, so triple the x, triple the y, 15 corresponds to, what is it? 15, 9. If we put 20, which is 4 times as much, that would be 12. If we put 100, which is 100 times as much, this would be 300. So No, wait a minute. If X was 100, that's what I meant to say. That's 20 times as much. So then this guy would have to be 60. Yeah, 160. There we go. All right, but what if we have some odd number, such as in this example? What is Y when X equals 7? Ugh. And most likely than not, I'm going to ask you questions that are not, a whole number multiple of the other of the initial input. Okay, so let's do this over here. Let's actually solve this equation. Here we have to set up an equation. All right. So first, we use the direct variation piece of information. That tells us that Y is equal to a constant X. That's what direct variation means. So whenever you hear direct variation, try to bring this back to your mind. We have this kind of thing. We do not know the constant of variation. All right. Okay, but they do give us initial information. When X is 5, when this guy is 5, Y is 3. Well, they're giving us the other way, but it is the same thing. When Y is 3, then X is 5. Okay, so that means we can solve this equation for K. Okay, so 3 equals K times 5, divide by 5, so K equals 3 over 5. So now we can go back and say, oh, Y equals, by the way, 3 over 5 times X. So this is the generic direct variation equation. This is the specific direct variation equation corresponding to this problem. Every problem has its own direct variation equation. So this is the one corresponding to this problem. Can this be equal to another problem? Perhaps, maybe. Maybe by coincidence, yes. But in general, no, we may not assume that. Okay. So for this particular equation, 3/5 is the constant that relates Y with X. All right. So now when they say, what is Y when X equals 7? So there's these problems of variation are actually two problems in one. On one hand, we have to find the constant, and then we have to find the X. Yep. Or rather, the Y in this case. Okay, so first we find the constant using the information they gave us. They gave us the 3 and the 5. And now we found the constant. Now that we have that, now we can answer the question, which is really straightforward. When X is 7, so now we plug in the 7 here. So Y equals 3 over 5 times 7, which is, of course, 21 over 5. So that is the answer for Y. And we're finished, done. Okay? But again, these are two problems. Example 3. Okay, so assume A, the letter A, and B are in direct variation, and B is 7 when A equals 5. So this is one big piece of information, well, actually two, direct, and they're giving us one output and one input. The question is, what is B when A? Now, the easy thing to ask would be when A is 10 or 15 or 20 or 25 or 30, some multiple of 5, because then we multiply the same number of ways with a 7. So when A is 10, B is 14. When A is 15, B is 21. 3 times as much, 3 times as much, 4 times as much, 20, 4 times as much, 28, and so forth. But then it gets weird if A is something like, I don't know, 13. So that's not it is not a whole number multiple of 5. The only thing we can say, there's something we can say, oh, there's a question mark. This is a question mark, there we go. The only thing we can say is, okay, 13 is between 10 and 15, so times 2 and times 3. So I know the answer is going to be somewhere between 14 and 21. That's the only thing I can say right now with this little information. Now, remember, every variation problem is actually 2 problems in one. So direct variation means, okay, we're going to set b equal to a constant times a, but we do not know the constant. However, they do tell us that b is 7, when a is 5. So we solve this equation and state that k equals 7 over 5. Watch out, it's very easy to mix those two and have 5 over 7 instead. I've seen that even in calculus. I've seen students, it is a mistake. Yeah, it's just a mistake, but be careful with that mistake. Anyway, so now we have the constant, and that means the equation for b and a is really 7 over 5a. That is the equation corresponding to this problem. See, they didn't give us the equation. They give us sort of what the equation kind of looks like, but they didn't give us the precise equation that works with this problem. We have to do some research to get to that point. Okay, now we got the equation, and now we can answer the question. What is b when a is, so the variable a, or the letter a, is 13? So all we have to do is plug in 13 in here, and so we have b equals 7 over 5 times 13, and let's multiply that out. 7 times 3 is 21, carry 2. 7 times 1 is 7, 8, 9, 91 over 5. Yeah, which is, by the way, 18.2, if I'm not mistaken. I'm just doing this in my head. 18.2, which makes sense because since this number is more than double but less than triple than the 5, the output should be more than double but less than triple than the 7. Double the 7 is 14, triple the 7 is 21. We get 18.2, it makes sense. So there is our output corresponding to 13. So that's how we solve problems of direct variation. Boy, this is getting not too bad, I think, I hope. Example 1, example 2, example 3, example 4. Now let's start working with inverse variation. Okay. Assume y and x are in inverse variation, and that y equals 20 when x equals 8. Okay, so let's make an easy problem and then a, and then a more difficult problem. So the first question I want to ask is, what is y when x is 16, question mark? Okay, now pay close attention to inverse variation. You know, I can see this in a multiple choice problem easily, where if you don't pay close attention to whether we have a direct or inverse variation, that will mess up your answer completely, totally, absolutely. I can see that happen. So pay close attention to whether we have a direct or inverse variation, because what I'm likely to do is to put inverse variation and then give you some answers that correspond to direct variation. Does that make sense? So I'm trying to see if the student is paying attention to whether we're asking for inverse or direct variation kind of solutions. All right. So inverse variation means that what happens to one of the inputs or outputs, the opposite is going to happen to the other one. So this is an easy problem because we don't really have to set up an equation. We can just use common sense. See, the input is 8. Now the input is twice as much. in inverse variation, that means that the output has to be cut in half. So just by using pure common sense and having a good idea of what inverse variation means, I know that when we double this has to be cut in half. So the answer would be y has to be 10, because double implies half. Double of one implies half of the other. Well, what is y when x equals, let's say, 40? Question mark. Okay, same principle. Okay, so the input that they give us initially is 8. We are quintuply or multiplying by 5 the 8 to get to 40. So 8 times 5 is 40. Now, if we were in direct variation, we would multiply by 5 and get 100. But no, don't do that, because we are in inverse variation. So since we multiply by 5 to get to from 8 to 40, what we have to do is divide by 5 the 20 to get down to 4. So when x equals 40, y equals 4. There. So the idea is when we multiply on one, we divide on the other. Okay, so far we're thinking, I got this, no problem. Yes, except, I mean, just using common sense is good, but what is y when x equals 17? All right. All right, now we have okay, this is not as easy anymore. That's why we need the algebra, because with easy problems, we don't need algebra. You know, you can just figure them out. But when the problem becomes more like this, then it's not obvious. Then we have to set up an equation. At least I have to set up an equation. Some people are really sharp and they can probably still figure it out. But I'd rather just set up an equation. Let's see. Okay, so y and x are in inverse variation, y and x. So that tells me that the equation that relates the two is some constant. We don't know what the constant is, divided by x. Okay. Okay. But we do have enough information to figure out what that constant is. You know, y is 20 when x is 8. So 20 is equal to a constant divided by 8. I'm going to continue up here. So we multiply by 8 on both sides of the equation. So the constant is equal to 160. So that means that the equation, this equation that relates x and y, is really y equals 160 over x. Yeah. And we can double check. When x is 8, 160 divided by 8 is indeed 20. So we're good. This equation corresponds to this problem. So we had to do some work just to get to the equation we're going to use. But now we're going to plug in 17. Oh, there's not much to simplify because 17 is a prime number and 17 is not a factor of 160. What I mean to say is there's nothing to simplify. So y equals 160 over 17, and that is our answer. Just plug in the 17 and there is nothing to simplify. So we are done. That's the kind of answer I expect. I'm a little curious to know what the number is, because the output here is 20 when x is 8. 17 is more than 8. It's double 8 and more. It's a little more than double. So this is a little more than double the 8. So I expect to have a little less than half the 20. if we were doubling, as in this case, the answer would be 10. But because we are doubling and adding one more to it, to the input, that means that we are not getting 10, we're getting less than 10. And I'm curious to know what this is. So I'm just going to take a regular calculator and divide 160 by 9. I'm sorry, I didn't mean to do that. 160 by 17. 160 divided by 17. I was thinking the answer in my mind was going to be 9 point something. That's why I incorrectly typed 9. But the answer is 9.41 and change. If we round it to, anyway, we're not going to round. I just wanted to have an idea. This is about 1.4, rather 9.4, which makes sense because it is less than 10. And since this number is bigger than 16, we were expecting a number that was less than 10. Not a lot smaller, but yet smaller. Yeah, inverse variation can be tricky. It can be very tricky, I think. So let's do example 5. Okay, so assume X and Y are in inverse variation, period. Okay. And Y is equal to 13 when X is equal to 17. Okay. So let's think of an easy question to ask. What would be an easy question to ask? Okay. What is Y when X equals 51, for instance? Well, something to notice is that 51 or 17 goes into 51 evenly, 3 times. If we multiply 17 times 3, we get 51. Okay, so this is triple the input. That means that because we have inverse variation, the output has to be divided by 3. It has to be a third of 13. So without doing much math, we just know the answer has to be 13 over 3. Yep. Another easy problem. Next, what is Y when X equals half of 17? 17 over 2. Well, if this is the input and we have the input and we have inverse variation, that means we have to double the output. We have to do the reverse. Y is double 13 is 26. Done. That's very simple because we're just thinking, hey, this is 3 times as much, so the output has to be divided by 3. We have inverse variation. If we had direct variation, triple this, and then you got to triple that. If we were to have this, then we would have to half the Y also. So if we were in direct variation and the input under this problem, and the input was 17 over 2, then the output would have to be 13 over 2. They have to be in this, they have to be, I'm trying to think of the word, treated. They have to be treated in the same manner. Half one, half the other, under direct variation. Under inverse variation, as the name suggests, we do the inverse, the opposite. So half one, double the other. But now let's do one that is really, really difficult. What is Y when X equals 3/4, 3/4? Oh, question mark and question mark. Okay, that's, okay, so we are now doubling the 17. 3/4 has no relation to, I mean, no, I don't see the relation. You know, it's not like 51 that is 3 times as much, or 17 over 2, which is exactly half of that. To go from here to here, who knows what we have to multiply by to go from here to here, and then we have to do the opposite, which is the reciprocal to get to to the output. Let's just set up an equation. And then to make things even worse, this is a fraction. In the other problems we did, there was no fractions for one of them. Okay, so inverse variation means set it up as y equals constant over x. Now we got to figure out this constant because this is a vague equation. It's not a complete equation for this problem because each problem has its own k. You know, in problem number 4, what was the k? If you go back to problem number 4, the k was 160. In problem number 3, what was the k? Did I lose 7/5? So that was a fraction. In problem number 2, did we have a k? Oh, it's up here. The k was 3/5. So 3/5, 7/5, 160, and who knows what's going to be here. So the k changes from problem to problem. Can two problems have the same k? Maybe, but we cannot expect that. We just don't know. Now it's easy to figure out the k. Plug in the 13 and the 17 respectively for y and x. So 13 is equal to k, which we do not know yet, over 17. Multiply those two. So I'm going to continue here. K is equal to 13 times 17. I typically do that by hand. And why not do that? I'm just going to do that here. 17 times 13, 51. 3 times 17 is that. And then 1 times 17 is 17. So we have 221. 3 times 7. Yeah, 3 times 17 is 51. 1 times 17 is 17. 1, 12, carry 1, 221. So K is 221. So the equation that relates X and Y in this particular problem is Y equals 221, divide that by X. Okay, we haven't started solving for the Y value for this X yet. We're trying to figure out the equation that works for this problem. Each problem has its own equation. Isn't that wild? But that's the way it goes. So now the complication here is that the input is a fraction. I'm very tempted to give you a problem where perhaps the k, in an assessment itself is a fraction. So you have to remember how to divide a fraction by another fraction. I don't know if I'll do that or not, but anyway. So in order to figure out the y value corresponding to the x value, we have to plug in 3/4 or 3/4 into x. 3 divided by 4. Whenever you have a fraction within a fraction, it is probably a good idea to put parentheses around the fraction because, let me step to the side for a moment. If you have two fractions, a divided by b divided by c, which one is the numerator or denominator of the other fraction? There's got to be some hierarchy. There are two fractions, but as is, this is completely and 100% ambiguous. Well, let's pretend the lines are exactly the same length, because typically the bigger line tells us which one is the bigger fraction. As is, so this is ambiguous. First, I just want to know that. Ambiguous, which means we don't know which one. Do we mean A is the numerator and the denominator is B over C? Or do we mean A over B and then the denominator is C? So to avoid complications, I typically put extra parentheses to make sure there's no confusion. If something math people do not tolerate very well is ambiguity. Yeah. Now, that doesn't mean we don't understand ambiguity. There are places where we do want to be purposely ambiguous. But generally speaking, when we are solving a problem, no. Or when we are checking solutions and such, no, we don't want to be ambiguous. Anyway, so here we got the fraction multiplied by the reciprocal. As you already know, I'm going to put a line to divide this column from the next column there. More. So we really have y equals 221 multiplied by 4/3. So that gives us 884, 884 divided by 3, which is a pretty big number. Um, Again, this is the final answer. Don't necessarily put it as a decimal. Sometimes I do that just to have an idea. Well, before doing that, I'm going to make sure that 4 times 21 is 884 because I did this in my head. I'm quite sure, but it doesn't hurt to double check. 221 times 4 equals, yep. And then if we divide by 3, we get a big number, 295, about 295. Now, don't put that down. It's a huge number, almost 300. So this is close to 300. So the question is, why so big? Does it make sense to have a big number? Well, think about the initial data. 17 down to 3/4, that's a huge reduction in size. From 17 to 3/4 it's a super shrink. 3/4 is 0.75, less than 1. 17 is almost 20 times as much. Okay. So the input got reduced significantly, quite a large factor. Well, that means that the output, because this got reduced, the output have to be expanded by a lot. That explains why we end up with such a big output here, because we are working with an inverse variation as opposed to a direct variation. Very quickly, let's do an example of joint variation and combined variation. Might just as well. 6. Example 6. Okay, so now we have to have 3 variables. So let's assume z varies. So we have to be more specific. Z varies directly with x and y. And, so comma, and z equals 10 when x equals 2 and y equals, let's put 13. What is z when x equals 3 and y equals 8? Boy, that is a complicated problem. Whoa. Okay. So when we have direct variation between just 2 variables, x and y, one doubles, the other doubles, that's pretty straightforward. Now, this is the weird part about this, the joint variation. Z varies with respect to 2 variables now. If this doubles, this doubles. If this doubles, that also doubles. If both double, then this quadruples. Then this gets multiplied by 4. If this triples and this doubles, then this one gets multiplied by 6. So we combine whatever happens with this along with whatever happens with that and multiply them together. And that's what happens to this guy. Yeah. So what is the equation? I haven't told you the equation. The equation that goes with this is z equals kxy. So instead of just y equals kx, now we have z equals kxy. So that is the equation that relates varies. Oh, I misspoke here. Varies jointly, not directly. Yeah, jointly is the word I was, or the adverb in this case, I wanted to use. Jointly with x and y. That means, and this is not completely incorrect because jointly means direct with x, while we're also varying directly with y. So there's two direct variations, and they compound with one another. This is the equation we use. And how do you know that? Because of the word jointly. Just like in the previous examples, we know we have direct variation because it's going to be spelled out, direct variation, or inverse variation. Now we have joint variation. We're going to go ahead and find the K right away. We do that by plugging the numbers that are given to us. 10 is equal to K, which we do not know the value of yet. X is 2 times 2, and Y is 13. So in other words, K is equal to 10 divided by the product of those two, which is 26. But always, always, always simplify. So that is 5 over 13. So now we have the equation corresponding to this problem. Remember, every equation has its own problem. We have a vague equation. How do we know that? Because of the word they're using, direct, inverse, jointly, or combined. So jointly means multiply everything across. Well, the z is the product of everything, all the other variables. That's what jointly means. All right, so our equation is z equals, now that we know k, 5 over 13 multiplied with x and multiplied with y. Typically, we don't put the dots like that. I'm just emphasizing. X is 3, y is 8. So 5 over 13 times 3 times 8. So 5 times 8 is 40, times 3 is 120. So the answer is 120 over 13, which is less than 9. No, less than 10, but not less than 9. So it's got to be 9 point something if I'm not mistaken. Does that make sense? Well, x got to be, what is the new x here? 3. So x got bigger, but y got smaller. So on the two together, we didn't go too far away from the original output, which was 10. So z is equal to this on joint variation. Example 7. What about combined variation? So assume z varies directly with x and inversely with y. Whoa. So directly with x means that if we double the x, we double the z. Triple the x, triple the z. But inversely with y, double the y, and we have to do half of z. So now we got the two of them combined. Okay. We haven't finished writing the problem because we need additional information, and we have to ask a question. There's no question to be asked here. I mean, there's no question yet. Assume z equals 10 when x equals 2 and y equals, let's make this confusing, 5. What is, okay, let's make two questions about this. Something easy. What is z, easy first? When when x equals 4 and y equals 10, question mark. Okay, this problem has a lot of parts to it initially. It may feel like it has a lot of parts, but just stay with it. Z varies directly with x. and indirectly with y. So keep that in mind. Directly with x, indirectly, inversely, not indirectly, inversely with y. Okay, so if we double the x, from 2 to 4, the output would double to 20. But if we double the y, then the output has to be halved. And they undo each other. So if we double the variable corresponding to direct variation, the output doubles from 10 to 20. If we double the variable that corresponds to inverse variation, the 20 that we got gets to be divided by 2, because doubling this means dividing by 2 on the output. So because we double from 2 to 4, we double the output from 10 to 20. Because we double the y from 5 to 10, we have to divide by 2 the 20 we got back to 10. So the answer is 10. I'm going to do one. Now, you can set up an equation if you want to. All of the problems that were solved by common sense can absolutely be solved with an equation. No problem about it. We can always do that. So you can always go back after we do a problem that is solved with an equation. You can always go back to this one and solve it with an equation as well. I'm just using common sense, but the equation will work just as good. B. So what is z when x equals 7 and y equals 13? Okay, now we got a difficult problem because we're not doubling the 2 or the 5. It's just some kind of weird proportion of the 2 and the 5. Can we figure it out, the answer, without an equation? I think so. I think there are some students who are really, really good at this, and they can do it. And that's really good. I typically can't in this case. Once it gets a little convoluted like this with weird numbers like that, then I have to really use the algebra personally. So what is the equation we're going to use? Z equals kx, remember that's direct, over y, that's the indirect. Isn't that interesting? Now we have a 1k. Don't get confused, please. We don't have 2k's. Same thing with the joint. With joint variation, we have a single k. 1k. That's it, not 2k's. Same thing here. There's only 1k. Some students may be thinking, hey, we got an x and a y, so we got to have 2k's. No, 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 no. 1k. That's it for the whole thing. Okay. Now let's figure out the k using this initial information. 10 to 5. 10 equals k times 2 divided by 5. Now we got to solve this proportion for k. Multiply by 5, we get 50. 50 equals to k. That means that k has to be 25. Again, multiply by 5. So 50 equals 2k. Divide by 2. 50 divided by 2 is 25. Okay, so this equation now becomes 25x over y. And now we can plug those numbers. Oh, before I do that though, let's pretend we couldn't think of this by common sense. We would still go through this process and end up with z equals 25x over y. I crossed this off not because it's wrong, but because let's pretend we couldn't come up with this using common sense. The equation will work. So put 4 for x. So 25 times 4, divide by y, which is 10, and that makes sense. 25 times 4 is 100. 100 divided by 10 is 10. which is the answer we got before. So that still works. We're going to plug in 7. So 25 times 7 divide by 13. And 25 times 7 is 175. So Z is 175 divided by 13. And there we have it. All right. Practice proportions, direct variation, inverse variation, joint variation, and combined variation. Now, in combined variation, we're not going to necessarily say, oh, we got a combined variation. We just say which one is direct, which one is inverse relative to Z. But we still end up with one constant. All right, we're going to stop the video here.